Good evening, everyone. Today we will present on the condition monitoring for oil paper insulated HV transformer, which is a focus on the partial discharge. So I am Chung Chee and with my two other groupmates, who is Mr. Megat and Morwinthren. Okay, so I think we are familiar about what is the definition of partial discharge during the class. So the partial discharge is a localized electrical discharge within the insulation, and it may be occur either near or away from the conductor. And the partial discharge does not fully reach the conductor, so it does not form a conductive channel between the electrode. And it occurs at the defects such as voids or bubble and etc. And it does not cause immediate failure, but the repeated of the partial discharge activity will slowly weaken the insulation system. And it is the activity that indicates the insulation degradation. The partial discharge starts when the local electric stress exceeds the insulation strength, and it can happen in solid, liquid, and gas insulation. So in solid insulation, partial discharge occurs in voids, and repeated partial discharge activity cause erosion and lead to electrical treeing and result in puncture. In liquid insulation, partial discharge happens in bubbles or particles. Repeated activity will form the streamer growth in liquid, and conductive path is created and leading to breakdown. However, in the gas insulation, the partial discharge will begins with an electron avalanche under high electric stress. This develops into streamer and spark, and the repeated partial discharge activity can cause the flashover. Okay, this slide shows 5 categories of the partial discharge based on the partial discharge occur within the insulation system. So the first one is the internal partial discharge. The internal partial discharge is the partial discharge occur inside the insulation, usually in voids or cavities. The second is the surface partial discharge. The surface partial discharge occur at the insulation surface where the electric field is non-uniform. The third one is the corona partial discharge. Corona partial discharge occurs in the gases such as the air when the electric field around the sharp edges and electrodes are very high. And the fourth is the laminated insulation partial discharge. This type of partial discharge occur in the layer insulation such as paper insulation. The uneven voltage distribution between layers create high electric stress. The last is the treeing. Treeing is the high intensity partial discharge, and it will form water treeing and electrical treeing inside the insulation. When this channel grow and become conductive, it will accelerate the insulation breakdown. So this is the slide show where the partial discharge can typically occur inside a transformer. So around the bushing entry and end chute areas, the electric field is high. So the corona type partial discharge can occur, especially near the sharp edges or air gaps. Inside the transformer, internal partial discharge mainly occurs within the oil paper insulation system. A small void between paper layers, narrow oil channel near spaces, or poor oil circulation can create high local electric stress and initiate the partial discharge. Surface discharge may also develop along the pressboard, barrier, and spaces, particularly when the moisture or edging affect the insulation surface. And lastly is the contamination, such as the particles suspended in the oil can further distort the electric field and trigger the internal oil partial discharge.
Good day, everyone. Thank you, Chee, for your brief introduction on partial discharge and where it would occur in a transformer. I would like to continue our presentation on discussing the governing international standards in partial discharge of a transformer. So for first, I would like to start with IEC. IEC 60270 is a global standard, and it gives us the definition of partial discharge intensity in the unit of picocoulomb, and it specifies on the test circuits and the calibration methods used for partial discharge in electrical measurements. So, and also there is IEC 60076. It is to identify transformer windings to the highest voltage of the equipment associated with the corresponding rated insulation levels. And this is applicable for single phase transformer and also three phase transformer. Next, I would like to move on with the IEEE. IEEE C57.113 states that it is the recommended practice for partial discharge measurement in liquid filled transformers. It provides a detailed guidance on noise suppression and also interprets the results specifically for liquid filled units. And IEEE C57127, it gives us the guide on detecting, locating, interpreting the sources of acoustic emissions from electrical discharges in the transformer. It gives us a definitive guide on using piezoelectric sensors to listen to the partial discharge and also mathematically locate the partial discharge inside the tank. Moreover, there is also CIGRE, where they have produced Technical Bulletin 681 to to discuss the improvements of partial discharge measurements in factory acceptance tests and also site acceptance tests. And this is all tests to be conducted prior to service. And there is also a modern guide on detailing how to use ultra high frequency sensors such as antennas for noise immune partial discharge detection, particularly useful for online monitoring. For Technical Bulletin 343, it recommends us the condition monitoring and also condition assessment facilities for transformer. It provides a industry guideline on installing ultra high frequency sensors, mainly through drain valves and also dielectric windows, and it also gives us the ways to interpret the data. I would like to move on discussing the detection techniques of partial discharge. First, through chemical monitoring. So, when we conduct dissolved gas analysis of the oil inside the transformer, partial discharge generally decomposes the oil and the paper, and it produces certain byproduct. For an example, in oil, when there is a detection of hydrogen and also methane, it gives us a clear indication that there are early signs of partial discharge. Whereas when there is ethylene, it, it shows that it is critical because it is showing that there is severe partial discharge happening inside, and it also indicates that there is a voltage breakdown happening inside the transformer, which causes arcing present in the transformer. So all this intensity of byproduct is then tabulated through using a dual triangle, where it can interpret the gas ratios and diagnose the partial discharge. Next would be through electrical detection. So as mentioned in IEC 60270, we use external coupling capacitors and also bushing tabs across a calibrated impedance. This calculation is extremely sensitive, as the partial discharge can be detected up to less than 10 picocoulomb, but this is highly susceptible to external electrical noises such as corona and radio waves. Moreover, there is also through acoustic detection, since partial discharge produce a mechanical shock wave that travels through the oil and hits the tank of the wall. We can attach piezoelectric sensors that can localize and also detect the intensity at a specific region of the tank. So hence we can specifically identify the partial discharge at a certain location of the tank. And finally, through ultra high frequency. So partial discharge actually generates electromagnetic waves in the ultra high frequency range of 300 megahertz up to 3 gigahertz. So when we install antenna in the drain valves or dielectric windows of the tank, this acts as a Faraday cage where the tank actually blocks external noises, making this method extremely accurate on online monitoring of the partial discharge. So thank you so much. I would next like to pass the floor to Megat.
Now I will share on prevention and control method of partial discharge within a transformer. On the first one, which is the electric field stress control, in general we have three strategies that we can do. The first thing is removal of sharp edges. This is straightforward, as the sharp edges will cause the concentration of electric fields, while on the next strategy is on adequate clearance. This also reduces the stress within the insulation. And the last is apply stress shields. Or the next strategy is voice, gas, and pocket elimination. Two things that we should be careful. The first one is on the good paper clamping and insulation fill up, which means whenever we stack up our paper to form an insulation within the transformer, we make sure the layering is being done properly so that there are no potential bubbles within that kind of layer. And while we filling the oil transformer with the liquid insulation, so the filling is being done through a proper and gradual so that the gassing activity does not occur. The things that we can do is on executing the vacuum drying or vacuum oil impregnation. And the next things that also on the prevention and control is towards the contamination and particle control. Whenever we assemble our transformer, we make sure the environment is clean from all any potential particles. And while the transformer is in service, things that we can do together with the vacuum drying or hot oil filtration scheme is on the filtration and contamination removal. Within this kit, typically there are 3 or 4 level of filtration that we can do, which is the first is, as we discussed previous one, is on the oil heating, which is to remove the moisture. Then the next one is on the degassing, which is removal of the gas. And the other two, one is on the filtration bubble and gassing control. So first thing that we can do to help on the reducing on the bubble and degassing is on prevention of hotspot and local overheating. This is because hotspot and overheating will cause the formation of bubbles, and this formation of bubbles will create the potential PD within the liquid insulation. The next thing that we should avoid is on the cavitation zone within the oil flow. So especially for oil cooling that use forced method ventilation, the cavitation might happen. So this kind of cavitation also will potentially cause the PD within the liquid itself. The last but not least on the transformer PD prevention and control is on the static electrification control. So it's can be done through the improvement of flow of path design, as well as ensure adequate charge relaxation and manage material interface and condition. The last part of this presentation I will share on the PD strategy for the transformer. So the first strategy that we can do whenever we execute the PD strategy is prioritizing and establishing the baseline for our transformer. So we will start with the goal and asset priority. Within this activity, we set our clear objective on how we're going to execute this condition-based monitoring approach. Typically, we will rank the transformer by its criticality. So this criticality can be ranked by several methods. Among things that typically people do is through the impacts towards the loads. For example, if the load is impacting on certain criticality, or transformer will deserve on the monitoring and control practice. So again, on the redundancy, if the systems does not have redundancy, or then it's also can be ranked up higher. The next thing is on the age and failure history. If the age of the transformer gets older, the probability of PD happening is also high. The baseline typically on the offline PD benchmark using IEC 60270. So this can be done during commissioning, during plant outage, or even after major repair. PD, we could not prevent PD due to the few factors. So as we have the baseline value, we can monitor whether the PD is increasing or maintained at the static level. We have the baseline value. We can set it on the frequency basis, on specific frequency. That frequency is determined by the itself. If the transformer is highly critical, the frequency can be much more frequent, maybe 2 years. Under the online PD detection, there are 2 methods that we can execute, which is with the for continuous monitoring or even the periodic scanning. So continuous monitoring, based on the ranking that we established just now, we can determine which type of transformers that we can put higher priority so that we can spend on the investment for the continuous monitoring. That on the sensor, there are several sensors that are available, especially for example, that we can use UHF for internal PD trending. And on the periodic scanning, so the rest of the transformer that not really on the high criteria metrics, we could focus on the periodic scanning, but of course high possibility of PD, for example on the cable termination, bushing, or even lead or exit turrets. So the idea for scanning as online method is quite prone to errors and noise. So we will clearly, based on the trend establishment. The escalation rules that we put here is whenever we trigger for the PD that we do online, we always need to confirm with offline strategy. Can be monitored through the PD if the PD become continuous and no longer intermittent, or the pattern become much more energetic and spread to establish across higher magnitude. So the sensors that we can use UHF or acoustic emission. We could confirm with both of the type of the sensors. On the other strategies is on to use acoustic emission to localize the PD, understand the source of the PD source, as well as confirm it with the construction drawings, whether it's near the HV land or near the bushing area or even near the winding itself. So I guess that's all that we can share.